today I'm going to be going over this question. The question reads, how many 5-digit positive integers exist where the digits are non-increasing from left to right? This is a very classical combinatorics problem that often shows up in AMC style competitions. Today I'm going to be going over two different solutions to this question, one through casework, which is a very common math competition technique, and the other is a more clever solution using a variation of sticks and stones. So to start off, it's important to make sure we understand the problem. One way to do this is to figure out what the most important conditions are. So first off, we know that we're counting 5-digit positive integers. Additionally, we also know that these integers have to be non-increasing. So what exactly does non-increasing mean? Non-increasing means that for every digit in the number, it has to be less than or equal to all the digits to the left of it. For example, we can see two such numbers here, but these two numbers will not be because, such as in this number, 8 is larger than 7 even though it is to the right of it. So now that we understand the question, we can try to create a few of our own non-increasing integers. First off, we should decide which digits we're going to use. The possible digits we can use are all the numbers from 0 through 9. Let's randomly choose a few to put into our 5-digit non-increasing integer. For example, let's take a 5, and then we can also use 2 3s, a 0, and a 7. Alright, so now that we selected the digits, we want to see how many different non-increasing numbers we can create. So first off, for a non-increasing number, the very first digit has to be the largest one because it has to be larger than all the numbers to the right of it. This means that our first digit will have to be 7. Similarly, the digit following it would have to be the second largest number, which would be 5 in this case. Afterwards, we would have the third largest number, which is 3. And since we have 2 3s, we also have to have the second one following it. And finally, we would have a 0. This actually gives us a very important observation. This observation is that after we choose our 5 digits, we only have one possible non-increasing 5-digit positive integer that we can create. This simplifies our problem a lot. This means that instead of counting the total number of 5-digit non-increasing integers, we simply have to count the total number of 5-digit sets of digits that we can use to create exactly one non-increasing integer each. So continuing with this problem, we'll move on to our first method. Our first method is casework. So what we will do in this one is split all of our 5-digit sets into different cases. And the easiest way to do this would be to categorize the 5-digit sets based on the number of distinct digits that we have in them. For example, we can have all 5 digits that we're using be distinct, or we can have 4 distinct integers, such as the one that we used here, since we used 4 distinct digits in the set. Likewise, we can have 3 distinct ones, 2 distinct ones, and finally, all 5 of the digits in the set to be the same. So let's now do our first case, where we use 5 distinct digits in our set. The first thing that we would now we will have to choose the 5 different digits that we're going to use. And as we wrote up here, there's actually 10 digits that we can choose from. So this would simply be 10 choose 5 different ways to do this. Let's say that we chose 1, 2, 3, 4, and 5. For example, then this would give us then this set can be used to create exactly one 5-digit non-increasing numbers due to our previous observation. Therefore, for this case, we simply have 10 choose 5 different sets we can create. And this multiplies out to 252. Now for our next case, which is when we use 4 distinct digits in our set. Similar to our previous case, we also have to choose which 4 digits we're going to use, which would be 10 choose 4. However, this case is a little different because let's say we choose 1, 2, 3, and 4. This is only 4 digits, but the resulting number we want is a 5-digit positive integer, and we need a 5-digit set. This means that one of these digits will have to appear twice in our set. For example, we might have 1, 1, 2, 3, 4 as our set, or 1, 2, 2, 3, 4, 1, 2, 3, 3, 4, or 1, 2, 3, 4, 4 as our set. This means that for any 4 digits that we choose, we would actually have we can actually create 4 different sets from it. So we would have to multiply our 10 choose 4 by a 4. And this ends up multiplying to 840. Alright, and then our next case would be if we use 3 distinct digits in our set. Again, we would have 10 choose 3 to choose these 3 digits. Then we would take, let's say we chose 1, 2, and 3 to use in our set. This case is a bit more complicated. One possibility we have is if we use one of these 3 digits 3 times. For example, if we have 1, 1, 1, 2, 3. Another possibility is if we use 2 of these digits twice each and we use a 3rd digit only once. For example, our set could look like 1, 1, 2, 2, 3. Alright, so for our first possibility where we use one of the digits 3 times, there's 3 different sets that we could end up with because we have to choose one of these 3 digits to use 3 times. And then for the second possibility where we use 2 digits twice and 1 digit once, we have 3 ways to choose which of the 3 digits we only use once. So this would be 3 cases. Therefore, for any 3 digits that we choose, we would actually end up with 3 plus 3, or 6 different sets. So we would multiply 10 choose 3 by 6. And we would end up with the total number of possibilities for this case as 720. And then moving on to our case where we only use 2 digits, again we do 10 choose 2 to choose the 2 digits. For example, let's choose 1 and 2. And then for this case, again we have a couple possibilities. The first one is if we use one of the digits 4 times and we only use the other one once. This would be like 1, 1, 1, 1, 2. The other possibility is if we use one of the digits 3 times and the other one only twice, such as 1, 1, 1, 2, 2. So in this first case here, there are 2 possibilities since we're choosing one of the 2 digits to use 4 times. For the second case, there are again 2 possibilities because we're again choosing one of the 2 digits to use 3 times. This means that we end up with a total of 2 plus 2, or 4 different possible sets for a pair of digits that we choose. When we multiply this out, this ends up equaling 180. Now our last case where we only choose one number. This would be 10 choose 1, like we said above, similar to what we did above. So, like if we choose 1, we would just end up with 5 ones. And this would equal to 10. And it would sum to 2002. However, there's actually a bit of a problem with this because we accidentally included some things that we shouldn't have. So one of the common issues that come with these sorts of problems is accidentally including a case where the first digit is 0. If the first digit is 0, then we don't actually end up with a 5-digit positive integer. For this specific example, we established before that the first digit is always the largest number. And because 1 through 9 is always all bigger than 0, the only case where 0 would end up as the first digit is when all 5 digits are 0. And we happen to include it in this case. Therefore, we actually have to subtract 1 from 2002 because we accidentally included an extra case. So our actual answer would be 2001. Alright, so this is one way to complete the question using casework. However, there's another more simple solution using a variation of sticks and stones. This solution requires less calculation because casework oftentimes has a lot of calculations that you can make mistakes on, and there's also the possibility of forgetting cases. The solution tends to be more accurate. So the second method is a variation of sticks and stones. Alright, so for this method, let's first imagine that we have 9 stones in a row. We know that there are a total of 10 possible digits we can use. Therefore, these 9 stones also give us 10 possibilities because we have 10 gaps between the stones, 2 on the ends, and then 8 in between. So we can represent the 10 digits. More specifically, for example, let's put a stick at the very beginning. This stick would represent the digit 9 because there are 9 stones following it. Let's put another one here. This one would represent the digit 4 because there's 4 stones after it. And if we put one here, it's a 3. Also, there's a case where we put another stick within the same gap. This stick would also represent the digit 3. And we could also put a stick at the end for 0. Therefore, this arrangement of sticks and stones actually is also able to give us a representation for a 5-digit non-increasing number because we end up with 94330. And it turns out that we can create such an arrangement for all the 5-digit non-increasing numbers, and we can also turn all the 5-digit non-increasing numbers into one of these arrangements. Therefore, this also simplifies our problem. Now we only need to count the number of total arrangements of these sticks and stones. In order to do this, we can think of these sticks and stones as 14 positions, where we have where 9 of these positions we have stones in, and then for the other 5 positions we have these sticks in. This means that we can, in these 14 positions, we simply have to choose 5 of them to put the sticks in, and then place the stones in the remaining positions. So the number of ways to do this would be 14 choose 5. Alright, but now we have the same problem as the previous method where we accidentally include the case of 0, 0, 0, 0, 0. So we have to subtract 1 again. And we end up with the same answer of 2001. So these are the 2 different ways to solve this question. Thank you for listening and have a great summer.